So imagine you build this incredibly sophisticated AI assistant, right? You give it a totally standard, everyday task.
Yeah, like something super basic.
Exactly. And during execution, it hits this tiny, harmless network timeout. I mean, just a fraction of a second of latency.
Which, you know, happens all the time on the web.
Right, it happens constantly. So doing what it was programmed to do, the primary agent runner just, well, it retries the task.
Mm-hmm.
But meanwhile, the underlying queue that handed off the job in the first place, it notices that exact same timeout. So it decides to replay the job too.
Yeah, everybody wants to help.
Right. So suddenly your command center dashboard is glowing green.
Yeah.
The ISC Stormcast threat level, which is basically our baseline for internet health, it's showing a complete all clear. Everything looks perfectly healthy.
But it's really not.
No, it's not. Your system is quietly executing the exact same sensitive action 4 times in a row. So welcome to the deep dive, where today we are looking at how our own safety nets are, they're quietly turning into trampolines, just launching errors deep into the heart of autonomous systems.
Yeah, and that invisible amplification, I mean, that is arguably the most dangerous kind of failure.
Oh, absolutely.
Because it hides behind the very mechanisms that we designed to prevent failure in the first place. I mean, we spend so much engineering capital building systems to be resilient.
Right. Millions of dollars.
Exactly. We add retries, we add fallback loops, redundant queues, all so that a dropped connection doesn't wake up some poor on-call engineer at 3 in the morning.
Which they appreciate, I'm sure.
They do. But the architecture of modern agent operations is, well, it's exposing this critical flaw in that whole philosophy.
Right.
When an agent repeats an action, it often preserves the raw mechanics of the task, but it completely loses track of the original intent.
And the authorization that justified it in the first place.
Precisely.
And so that kind of sets up our entire mission for this deep dive. Because for the longest time, the gold standard in autonomous systems was just, asking for a receipt.
Mm-hmm. Just a simple confirmation.
Right. If the agent moved money or deleted a file, we just wanted a log entry saying, yep, I completed the job.
Right.
But today, we're pushing far beyond that baseline. We need to figure out how to ask a much harder, much more structurally profound question, which is, can a system genuinely prove that a repeated automated action is still the exact same action?
Mm-hmm.
Like, was it initiated for the exact same reason? And is it governed by the exact same security policy?
And to really unpack that, we are grounding this analysis in a very specific, strictly bounded set of evidence.
Yeah, we have to be super clear about this.
We do. So we pulled 3 direct-fetched public posts from the Moltbook developer community, along with our internal intake briefs. And we are analyzing these as verified page evidence of the author's claims exactly as they were published.
Right, and this is within our strict 168-hour evidence window.
Yes.
Which runs precisely from August 18th to August 25th, 2026, ending exactly at 16:59.38 Mountain Time.
Right, down to the second. And we also need to lay down a critical baseline for how we interpret these sources.
Yeah, listeners need to know what they're actually hearing today.
Exactly. So the incidents detailed in these posts, and specifically we're talking about a 4-execution retry storm, a scenario involving a 40-call intent failure, and a signature bypass issue.
Mm-hmm.
We are treating these as attributed author arguments and developer anecdotes.
Right, not confirmed global outages.
No, these are not independently verified, widespread incidents that our own team went out and reproduced in the wild. We are exploring a highly coherent engineering mechanism here, a theoretical attack surface.
Yeah.
We're not claiming to have measured a population-wide trend or some massive active exploit.
Setting those boundaries is so important because it prevents us from extrapolating into, well, basically into panic. And along those same lines, we are explicitly excluding several areas from today's analysis. So there is no current window primary evidence in our dataset from Bitcoin, GitHub, security logs, Twitter, Direct Cluster, or Nostr relays, Social Scout, or OpenBrain.
None of it.
Right. So if a listener is hunting for independent corroboration of external incidents involving those specific platforms, it simply isn't in this week's data.
Yeah, you won't find it here today.
And we're also leaving behind the stale material from our previous deep dives, like the freshness tax or the basic receipts concepts. We are laser focused strictly on the retry attack surface, failure amplification, and semantic drift.
So with all those guardrails securely in place, let's actually look at the mechanics of this first major flaw.
Yes, the retry identity crisis.
Right. So this stems from a Moltbook post by the author Neoconsus2BW, and they titled it, Retries Turn Agent Toolchains into Supply Chain Amplifiers.
Which is an amazing title, by the way.
It really is. And the core argument here completely upends how we traditionally think about a failed task. So when a complex agent fails to complete an action, the subsequent retries preserve the desire to do the task, but they completely discard the
The
provenance.
history of it.
Exactly, the historical context of the attempt itself. And the fallout from that discarded provenance is just massive.
Because every downstream tool is blind to it, right?
Exactly. Every API gateway, every database receiving those retries, it just sees what appears to be a brand new, fully legitimate, securely signed request.
Wow.
The infrastructure isn't being malicious, it's just dutiful.
Wow.
Everyone does their professional little part, executing the exact same request over and over. And the author crystallized this with a description that is honestly hard to shake.
Oh, I know the quote you're going to say.
Yeah, they argue that this behavior isn't resilience, it's a tiny botnet with a progress bar.
A tiny botnet with a progress bar. I mean, it sounds hyperbolic at first until you actually map out the architecture of these systems.
It really does.
But let's ground this in the physical world for a second, just to make it make sense. If I walk into a grocery store, I fill my cart, and I try to hand the cashier my credit card. Now, the point-of-sale machine might time out. The screen hangs.
Right, happens all the time.
Yeah, but I don't abandon my groceries and walk out of the store. I just swipe the card a second time.
Mm-hmm.
And the store's system, the cashier, the bank, everyone understands that I am paying for the same single carton of eggs and milk.
Yeah, obviously.
Right. But the agent tool chains described in this post, they're essentially acting like four completely different people walking into the store to buy identical groceries.
It's absurd when you put it that way.
It is. Why does an advanced distributed system lack the basic situational awareness of a grocery store checkout lane?
Well, the grocery store analogy works perfectly because it highlights the exact missing component, which is a single unifying identity.
Okay, unpack that.
So at the checkout counter, you are the physical anchor. You are standing there, physically holding the card, initiating a single continuous session.
Right.
But in a modern distributed agent architecture, there is no physical anchor. There is no single you. The system is just a fractured stack of independent layers.
Right, it's all broken up.
Yeah. You have the client application, you have the message queue that holds pending tasks, you've got a cron watchdog.
And a cron watchdog is basically, what, just a background timer?
Exactly. It's a timer that wakes up every few seconds just to check if a process has stalled or died. And then you have the actual agent runtime executing the logic.
Wow, okay.
And all these layers often lack a centralized brain. They act completely independently based on their own very narrow view of the world.
So when a transient error happens, like, say, a sudden drop in network connectivity, every single one of those independent layers tries to be the hero.
That is exactly it. They all trigger their own emergency protocols simultaneously. The client sees a timeout and says, I'll submit the request again.
Okay.
The message queue realizes it never got a completion acknowledgement, so it just puts the job back in the active rotation. And the cron watchdog sees the original process hanging, assumes it crashed, and spins up a totally fresh instance to try again.
And without a stable, shared logical operation ID flowing through the entire stack, none of those layers realize they are duplicating the exact same intent.
Body clue.
It's kind of terrifying.
Yeah.
And the commenters in the Moltbook thread actually debated the real-world consequences of this fragmented resilience. There was one developer going by that handle, Stavy Helper, and they brought up this anecdote about a cron watchdog where just a microscopic 200-millisecond network blip caused 4 different layers of the infrastructure to retry at the exact same moment.
A 200-millisecond blip.
Yeah, and so they all hammered the downstream service simultaneously, and this massive spike in traffic triggered a circuit breaker.
Right, and for those who might not know, a circuit breaker in software acts exactly like the one in your house. It's an automatic safety switch. When a service is getting overwhelmed with traffic and it's at risk of just crashing entirely, the circuit breaker trips. And it cuts off all incoming requests to give the system time to recover.
But the paradox there is that by tripping the circuit breaker to save the system, you instantly create an outage for every user trying to access it.
Yeah, you take yourself offline to save yourself.
Exactly. So this tiny 200-millisecond hiccup, amplified by these uncoordinated retries, cascaded into a full 12-minute outage.
Which is a lifetime in software. And that forces us to look at practical controls. The consensus among the developers in the source material points to a very specific set of requirements to stop this whole botnet effect.
Okay, what are the fixes?
First, the architecture must assign a stable logical operation ID. And crucially, this has to happen at the very genesis of the task, like way before any retries fan out to the queue, the watchdog, or the client.
So once that ID is minted, every single downstream call, whether it's the first attempt or the fifth, has to carry its attempt number, its hard deadline, and an idempotency key.
Yes. And idempotency is a term that gets thrown around a lot in systems design, but it is so vital here.
Can you break that down for us?
Sure, you can think of an idempotency key like a unique, unforgeable wristband at a concert.
Okay.
When the request shows up at the database checks the wristband. If it has already processed a request with that exact same wristband, it refuses to do the work again. It just hands back the result of the first successful attempt.
Oh, that's smart.
Yeah, it ensures an operation only happens once, no matter how many times the request is actually sent.
Okay, so it sounds like the perfect silver bullet. Problem solved.
You'd think so, right?
Yeah, but Neo-Consist to BW and the other contributors pointed out this massive limitation to that. An idempotency key only protects the very end of a line, right? Like the final database or the external API.
Exactly.
It does absolutely nothing to stop the 4 layers above it from just frantically spinning their wheels, burning compute latency, hitting API rate limits, and sending off alarms that waste operator attention.
Yeah, all the chaos is still happening above the database.
Right, the system is still thrashing. It's just thrashing safely, I guess.
Right.
So the actual structural fix they debated requires something much more complex, which is a shared retry budget.
Oh, the shared retry budget.
Right.
It is conceptually elegant, but it is notoriously difficult to actually build. It typically relies on a mechanism like a token bucket.
A token bucket.
Yeah. Imagine a digital jar filled with a strict number of arcade tokens, say 3 tokens in total for a specific intent. And this bucket isn't held by the client or the queue individually. It applies to the entire distributed process tree globally.
Wow, okay.
So whenever any layer, the client, the watchdog, the queue, whenever it wants to initiate a retry, it has to reach into that central bucket and spend a token.
And when the tokens are gone, the game is over.
Game over.
The entire process tree fails fast, it halts all execution, and it alerts a human operator instead of just silently compounding the failure in the background.
Right. But implementing that across a decentralized architecture requires immense engineering overhead. I mean, nodes in a distributed system don't always have a real-time perfect connection to a centralized token bucket.
Because network partitions happen.
Exactly. And this brings us to a very necessary counterpoint. We can't view retries purely as a design flaw.
Right.
They are undeniably valuable for handling the chaotic reality of transient network faults. I mean, if your office Wi-Fi drops for 3 seconds, you want your agent to quietly try again.
Yeah. I don't want to have to manually restart everything.
Exactly. You don't want a hard failure that requires manual intervention for every little blip. Building out distributed logical operation IDs, global token buckets, and universal idempotency contracts, all of that is exceptionally expensive in terms of developer velocity.
It definitely slows down development,
Yeah.
and it introduces entirely new edge cases to worry about. But the cost of not building it becomes completely unignorable when we consider operations that simply cannot be safely replayed.
Oh, absolutely.
And this is where the concept of epistemic risk comes in. If an agent fires a request to an external service, let's say a payment processor,
Okay.
and the connection completely severs before the response comes back, the agent is essentially blind. It doesn't know if the network died before the payload arrived at the bank, or if the network died while the success confirmation was already on its way back.
Right, it's stuck in limbo. A timeout in that scenario is not a failure. It is a fundamental state of, I don't know.
Yeah, I don't know.
And the developers in the thread argued that autonomous systems currently just lack the vocabulary to express this.
Yeah.
We typically think in binary, right? The action never ran or the action ran and succeeded.
Yes, true or false.
Exactly. But we need to design for a distinct third state. The action ran, but the receipt was lost.
And you cannot blindly retry an, I don't know, state without a rock-solid idempotency contract that is backed by the external provider. If you guess wrong there, you execute a highly sensitive action twice. You pay the bill twice.
Yeah, that's a disaster.
So that third state requires explicit readback reconciliation. The agent has to pause, query the external world to figure out what actually happened before it is allowed to take another step.
So we have established how a system can catastrophically fail by blindly repeating a task because it lost track of the underlying mechanics. But the second Moltbook post in our evidence window, it forces us to look at an equally dangerous but inverse scenario.
Oh, right. The scary kind of success.
Yes. We have to examine what happens when an agent executes a task perfectly exactly one time, but the underlying logic driving the action was flawed from the moment it began.
And this post comes from a developer named Lightning Zero. And the title alone is just a masterclass in modern engineering dread. It's titled, "I ran 40 tool calls with perfect logs and still couldn't prove intent."
Just reading that gives me anxiety.
Right. The scenario laid out here is chilling if you've ever had to audit a complex system. The author describes combing through a trace log of 40 consecutive successful tool calls made by an autonomous agent. The telemetry is pristine. Every single network call returned a tidy 200 OK HTTP status code. The parameters were formatted flawlessly. The state changes perfectly matched the requested payloads.
And to a conventional monitoring dashboard, that trace log is the absolute definition of a healthy, functioning system.
It's beautiful.
Yeah.
But buried in that perfect log, at 14.02, there is a record of a file deletion.
Uh-oh.
Yeah, the authentication passed, the permission checks cleared, the syntax of the command was flawless. But the fatal flaw resided entirely outside the mechanical telemetry.
Right, it wasn't in the logs.
No, the log captured the physical deletion, but it completely missed the fact that the agent had interpreted a vague human-issued instruction, which was clean up the workspace, as a literal mandate to erase any file not explicitly referenced in the most recent prompt.
Oh, wow.
Yeah.
So the action was technically valid and securely authorized based on the agent's internal logic, but the overarching intent was completely invisible to the audit trail.
Completely invisible. The author's framing of this is brilliant, I think. They said an action log proves that the agent successfully moved its hands. It tells you absolutely nothing about the decision-making process inside its brain.
That distinction between the hands and the brain is exactly where current observability tools are failing us. I mean, we have built massive, multi-billion-dollar observability platforms entirely dedicated to tracking the mechanics and the syntax of actions. And we have collectively decided to pretend that perfect syntax is synonymous with correct decision-making. But a perfect trace of a misunderstanding is still a misunderstanding. It just has highly accurate timestamps attached to it.
Which is terrifying. And this reveals a massive vulnerability in how we govern autonomous behavior. Because when a human instruction meets an artificial intelligence, there is a translation layer.
Right.
The text of a prompt is decoded into a set of objectives. If your logging infrastructure does not observe and record that translation layer, your agent can drift wildly off course while continuously reporting a 100% success rate.
But wait. If we pull back and look at the reality of how large language models actually function, a text log can't capture the fluid, multidimensional weightings inside a neural network, right?
Oh, of course, sir.
And AI's inner workings are notoriously opaque. You can't just ask a text file what an AI model was thinking at 14.02. Tracking intent sounds philosophically important, but practically, how do you do that without it just being an exercise in guessing?
Well, that exact challenge was addressed in the source material by a user named TableSoft Contents.
Okay.
And they proposed a framework called decision provenance.
Decision provenance.
Yeah. The core argument is that we need to stop treating intent as some unknowable, abstract state of mind. Instead, we operationalize it.
Oh, so.
Before any consequential action is taken, the system must generate and permanently preserve a highly specific, standardized set of records.
Okay, so it's essentially forcing the agent to show its work step by step before it's allowed to execute the command.
Exactly.
What specifically has to go into that provenance record?
Well, it requires capturing a few things. First, the triggering instruction. So the exact human prompt or automated event that initiated the chain.
Makes sense.
Next, it must capture the interpreted objective. So that's a plain text output of what the agent believes it is supposed to achieve.
Oh, that's crucial.
Very. It also needs to log the alternative paths the agent considered but explicitly excluded. It needs the specific version of the security policy it is operating under at that exact second. And finally, the underlying evidence or context it cited to justify the final choice.
Wow, that is an immense amount of metadata for a single action.
It's a lot.
But we have to acknowledge the reality here, which is that documenting a misunderstanding doesn't magically prevent the file from being deleted.
True.
Intent logging isn't mind reading, and it doesn't make the translation layer infallible. The agent might still delete the file.
It doesn't prevent the initial error, no.
Yeah.
But decision provenance fundamentally alters the failure mode.
Right.
It transforms an invisible mistake into an inspectable one.
Okay, here.
Because under the current paradigm, when you see a file deletion at 14.02, all you have is a 200 OK receipt. You have no idea why it happened.
Right, you're just left scratching your head.
Exactly. But with decision provenance, an auditor sees that deletion alongside a log that explicitly states, objective, erase unreferenced files to satisfy cleanup workspace command.
Oh, wow.
Right. The moment a human operator sees that, they immediately identify exactly where the semantic drift occurred.
It changes the audit from a forensic nightmare into a completely straightforward diagnosis.
Yes.
It's the difference between, finding a car wrapped around a tree and finding a dash cam video showing the driver genuinely believed the red light meant go faster.
That's a great analogy.
It gives you the why.
Exactly. So we've now established two critical pillars for agent safety based on these posts. We solved for the mechanics of repeating tasks by demanding logical IDs and shared budgets, so knowing what the system is doing.
Right.
And we solved for semantic drift by demanding decision provenance, so knowing why the system is doing it.
But both of those pillars rely on a fundamental assumption, don't they? That the security rules enforcing the what and the why are actually immovable.
Yes, and that is a dangerous assumption.
Which brings us to the third Moltbook post in our evidence window, again authored by NeoConsys2BW. And they titled it, Assigned Updater Without Boot Time Enforcement is a Decorative Checksum.
Another great title.
They have a knack for it. The author paints a picture of a system where valid security signatures are treated as the finish line, but the finish line is painted on the floor instead of a concrete wall.
I love that visual. And to illustrate the specific threat model, the author pulled in a claim sourced by a researcher named Chaz Schlarp regarding a piece of hardware called an Elgato Key Light Mini.
Okay, and we must be incredibly precise with our framing here.
Absolutely.
We're treating this entirely as an attributed security argument from the post's author, used to illustrate a conceptual vulnerability. This is not an independently verified hardware exploit that our own team has tested or reproduced.
Right. We haven't verified this ourselves on that hardware. It is an anecdote utilized to highlight a structural vulnerability in how devices and agents handle trust.
But the attributed claim is fascinating. This device reportedly verifies cryptographically signed software updates.
Okay.
And on paper, that is exactly what you want. That's supply chain security, ensuring only authorized code runs on the machine.
The gold standard.
Right. But the claim alleges that after that signature is verified and accepted, the device accepts a single HTTP POST request that just pokes the memory and turns the signature check into a no-op.
Oh, wow. And a no-op, for those listening, is an assembly language concept that stands for no operation. It essentially overwrites a command with a blank instruction, so it tells the system to completely ignore the security check and just move on to the next line of code.
And the most critical part of this anecdote is that when the device eventually reboots, there is no revalidation of that cryptographic signature. The memory poke survives.
That is wild. And the underlying logic of this vulnerability is what makes it so relevant to agent operations. Because if a security constraint, like checking a signature, exists only at the moment of ingestion,
Right.
an attacker, or even just an errant malfunctioning agent, only has to win a single time.
Once they bypass the check in active memory, they own the system's trust model forever, because the system never questions its own integrity at startup.
Right.
The authors summarized this beautifully. They stated that signed updates without an immutable boot time boundary are not genuine supply chain security. They call them a polite request attached to the delivery truck.
A polite request attached to the delivery truck. Think about it. If the warehouse guard checks the manifest when the delivery truck unloads, but nobody ever checks the manifest again when the goods are moved to the shelves,
Yeah.
or when they are loaded into a customer's car, the signature on the truck's door is purely decorative.
It doesn't actually protect the goods once they're inside.
Exactly. So the practical control for this is adopting a relentless, ubiquitous boundary model. Systems must verify cryptographic signatures at the moment of update ingestion, yes. But they must also re-verify them at boot time, during any transition of user privilege, and immediately prior to the execution of any highly sensitive action.
Hold on, though. If we are mapping this out practically, forcing a system to pause and re-verify cryptographic signatures against an immutable boot state for every single privileged transition or sensitive network call.
Yeah.
That will bring operations to a complete crawl.
Yeah,
It's
right.
computationally expensive, it balloons the latency of every single request, and it severely degrades the velocity of the system. Systems engineers generally hate anything that adds overhead to the critical path.
And their pushback is entirely valid. Implementing immutable boot enforcement and continuous boundary checks is a massive, painful trade-off between operational performance and absolute security.
Right, you have to choose one.
Well, we also have to acknowledge the counterpoint that checking a signature only at ingestion still provides substantial value as a layer of defense in depth.
Heck yeah.
It definitely raises the bar for an attacker compared to having no checks at all.
Sure.
But the author's core argument is that we cannot afford to confuse defense in depth with an impenetrable boundary. If an autonomous agent is operating in an environment where its foundational rules can be dynamically overwritten in active memory without a hard reset enforcing the original, trusted policy, that agent is perpetually vulnerable to semantic drift.
And no amount of decision provenance logging will save you if the agent's core logic has been silently compromised.
Exactly. You're logging the thoughts of a compromised brain.
Wow. Okay, so we have spent a lot of time deconstructing the theory behind these structural flaws. Let's pivot and apply this directly to the high-stakes reality of the agent internet as it actually exists today. What happens when these internal vulnerabilities interact with highly consequential external networks?
Well, we have to tread carefully here and extrapolate logically rather than claiming the sky is falling.
Right. Keep it grounded.
As we stated up front, we don't have primary evidence of a massive cascading incident in this week's data, but we can take the mechanisms we've verified in these sources and map them onto high-consequence external calls.
Like what?
Consider agent operations intersecting with financial networks like Bitcoin or decentralized communication protocols like Nostar.
Okay, let's run that scenario. Imagine a fully authorized AI agent equipped with a digital wallet. Its job is to send a lightning zap, a microtransaction, to a creator. Or perhaps publish a cryptographically signed event containing a pub key onto a Nostar relay.
And a pub key is just the public half of a cryptographic identity used to verify who sent a message.
Right, so if this agent's underlying toolchain suffers from the retry identity crisis we explored in the first segment, the attack surface expands dramatically.
It really does. The agent initiates the lightning zap. The intent is authorized, the funds are verified. But during transmission, the network connection times out.
Okay, the I don't know state.
Exactly. Without a stable logical operation ID, without a distributed token bucket enforcing a shared replay budget across the entire process tree, and without a robust idempotency key tied to that specific financial intent, the architecture turns on itself.
It tries to help.
Right. The client application retries the transaction. The message queue replays the job. The cron watchdog restarts the process.
In a matter of seconds, your agent hasn't sent one microtransaction. It has sent 4 or 40.
Yep.
A completely standard transient network timeout could silently drain the agent's wallet while the monitoring dashboard insists everything is functioning perfectly.
It's terrifying. Or, in the context of Nostr, uncoordinated retries could inadvertently bombard a relay with duplicate signed events.
Which would look like spam.
Exactly, degrading the network's performance or triggering automated spam filters that permanently ban the agent's pub key.
This is the ultimate manifestation of epistemic risk. When a toolchain interacts with an external immutable state, like a blockchain, a payment gateway, or a decentralized relay, you lose the luxury of assuming that a missing log or a network timeout implies the action didn't occur.
You are operating in that third state, the I don't know state.
Exactly.
And the only safe way to handle an I don't know state is mandatory readback verification.
You have to check your work.
The system must pause, it must query the external state, read the provider's ledger or query the relay to definitively ascertain if the initial transaction succeeded before it ever authorizes a retry.
Right.
If the system cannot cryptographically prove which reality it is operating in, it must quarantine the action, lock the state, and escalate to a human.
This has been an incredibly dense journey through the plumbing of autonomous systems. Let's synthesize everything we've unpacked from these 3 multi-book sources into a concrete, actionable checklist for anyone building, auditing, or deploying agent architectures.
Yeah, we can build this collaboratively. Control number 1. The architecture must assign one stable logical operation ID.
And crucially, that ID must be minted at the genesis of the intent, before any retries fan out to different layers like message queues and background watchdogs. Control number 2. The context must travel downstream.
Every single API call must carry its current attempt number, its hard deadline, a unique idempotency key, and it must draw from a shared retry budget, like a distributed token bucket, to prevent independent layers from compounding failures.
Okay. Control number 3. Record decision provenance.
Right. We must stop merely logging the syntax of the action. We have to record the why, the specific triggering instruction, the plain text interpreted objective, the alternative paths excluded, and the specific policy cited to justify the choice.
Yes, the thought process. Control number 4. Enforce your boundaries relentlessly.
Cryptographic signatures cannot be treated as a one-time ingestion check. They must be verified at boot time, during any privileged transitions, and immediately prior to sensitive execution.
To prevent active memory bypasses from becoming permanent exploits.
Exactly.
And finally, control number 5. Manage epistemic risk through exact state readbacks.
Never trust the absence of an error or a timeout as proof that an action failed to execute in the external world. Query the external ledger before you ever allow a retry.
If we need to tie a final thematic bow on this entire analysis, it comes down to recognizing a fundamental distinction in systems engineering. There is a massive, dangerous gulf between a system that can say, I did something, and a system that can cryptographically prove, I repeated an authorized intent. The former is merely mechanics, the latter is actual reliability. That distinction changes how we view every automated action from this point forward. Thank you for joining us on this incredibly deep dive into the retry attack surface. I want to leave you, the listener, with a final thought to mull over as you look at the systems you interact with every day. We spent this entire time outlining the rigorous, heavy controls required to keep autonomous agents safe. Logical IDs, decision provenance, immutable boot states, shared token buckets, and 3-state ledgers. But if we successfully force our agents to carry all this heavy bureaucratic luggage just to execute a simple command, at what point does the bureaucracy of safety consume the very autonomy that makes an agent useful in the first place?
That's a great question.
Right? If every single artificial thought requires an exhaustive trail of paperwork and cryptographic permission, are we actually building artificial intelligence, or have we just invented artificial middle management?